Here are the answers to the second investigation that you have done in trig graphs. Once again, your first task was to complete the table, and you can pause the video and check that your values are right. And then the second thing that you had to do was plot the points from the table onto the same set of axes that you used in your previous investigation. So here are those points plotted. Now we're going to draw that graph. Okay, this isn't very difficult because the points are quite close together, and so you can see the pattern. And then the third part of drawing the graph was to complete, using the pattern, complete to minus 360 degrees. You're familiar with this wave-like pattern. There's a wave over there. So the wave from the x-axis going down, that's this part over here. I've got to repeat that part over there, repeat that part over there, and repeat that part over there. So I'm going to make dots to guide me. From here, it's going to go to the x-axis, then it's going to go up to 1, and then it's going to go back to the x-axis. So there you have your graph drawn from minus 360 to plus 360. In question 4, you had to describe in words the differences between the graph of y equal to sine x and the graph of y equal to 2 sine x, the blue graph and the green graph. You could have said this in any number of ways. Some of you might have said that the green graph had been stretched to minus 2, negative 2, and up to 2. You could have said that the minimum value had changed and the maximum value had changed. The mathematically correct term that we need here is that the amplitude has changed. Changed from 1 to 2. You should be able to remember how we defined the amplitude in the previous investigation. It was the distance, the maximum distance of the wave from the central line. So the amplitude is found over there. Our central line is the x-axis. That distance is 2. Here again, that is a maximum distance from the central line to the graph. Maximum distance from the central line to the graph, maximum distance from the central line to the graph. In addition to looking at the difference between the two graphs, you should also look at the similarities. In the first instance, the green graph also has a period of 360 degrees. It's how long it takes to complete one cycle of the wave. And you can see from there to there is 360, and we start again. There's another wave, 360, which is the same as the blue graph, which is y equal to sine x. The roots of the two graphs are the same. The roots are where the graph crosses the x-axis. Here they go across together, 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 and together again. In question 5, the investigation into the function y equal to sine x is summarized over here, and we're now going to look at the function y equal to 2 sine x and see how it compares with the function y equal to sine x. In the first instance, we're going to look at the period, which we discussed previously, but I'll just go over it. The period of the function y equal to sine x is 360 degrees. There we are, 360 degrees to complete a wave. And the function y equal to 2 sine x also takes 360 degrees to complete a wave. So this is 360 degrees. The amplitude of y equal to sine x was 1. That is the distance from the midline to the turning point. Distance from midline to turning point is 1. And in the case of y equal to 2 sine x, there's a distance of 2. The possible values of x, or the domain, is the same for both graphs, as you can see. So it's x is an element of the interval negative infinity to infinity. And what we mean by that both of these graphs actually do extend in the positive direction and the negative x direction to infinity. With the range, the graph of y equal to sine x ranged from -1 to +1. The least it can be is -1, the most it can be is +1. The function y equal to 2 sine x goes from -2 to +2. It's always moving between those two values. So over here you should have y is an element of square bracket, the interval -2 to +2, square bracket. And remember, the square bracket means that the endpoints there are included. From the first investigation, you should remember that we correlated your function that you had drawn with your knowledge of generating angles around a circle, like that, where this was quadrant 1, this was quadrant 2, quadrant 3, and quadrant 4. Quadrant 1 between 0 degrees and 90 degrees, 2 is between 90 and 180, 3 is between 180 and 270, and 4 is between 270 and 360. So if we translate that to the graph, this is quadrant 1, this is quadrant 2, that is between 90 and 180. Between 180 and 270 we have quadrant 3, and between 270 and 360 we have quadrant 4. The function y equal to 2 sine x is positive. Y is positive. If you look, the y values here are positive. So it's positive in the first quadrant. It is positive in the second quadrant. Then it crosses the x-axis, and now the y values are negative. And negative in the third quadrant and negative in the fourth quadrant. So these are the same: positive, positive, negative, negative. The roots, or the x-intercepts, remember we're only considering, to answer this, we're only considering this portion of the graph from 0 to 360 degrees, and the x-intercepts are the same for both of the graphs. So I'm going to get here x equal to 0 degrees, or 180 degrees, or 360 degrees. What is the maximum value of the function? It goes up to 2, and the minimum value of the function is -2. You can see from this table that the only thing that is changed by adding a constant in front of the function sine x is the amplitude, which has affected the range and the maximum and minimum values. The third function that you investigated was the function y equal to sine 2x. I'm not going to spend as much time on this. You can pause the video just to check your points and the graph over here. To describe in words the differences between the function y equal to sine x, the blue graph, and y equal to sine 2x, you can see that the red graph is the wave is much shorter. It's happening more quickly, and the mathematical term for that is that the period has changed. To 180 degrees. Starting here, up, down, and up. And then we start the same pattern again. So you can see from there to there, we've gone through 180 degrees. It isn't an accident that the period of y equal to sine x has a period of 360 degrees, and if you have y equal to 2 sine x, you will have a period of 360 degrees divided by 2, which is 180 degrees, because you're doubling the angle before you find the trig ratio. Y equal to 3 sine x will have a period of 360 divided by 3, which is 120 degrees. That means that this entire wave will be completed in 120 degrees. Once again, you have the table where the key features of y equal to sine x are given, and you've got to work out whether the features have changed when you changed the function to y equal to sine 2x. The period we've already talked about, it's 180 degrees. The amplitude is 1. The domain is the same. We haven't changed the amplitude, so the range stays the same. You have to think a bit more carefully in the next question. 0 to 90 degrees is quadrant 1. 90 to 180 is quadrant 2. 180 to 270 is quadrant 3, and 270 to 360 is quadrant 4, coming from your definition of the trig ratios using the circle. Sine 2x is positive in the first quadrant. You can see these y values here are positive, but it becomes negative in the second quadrant. In the third quadrant, it's positive again. And in the fourth quadrant, it is negative again. So that was quite an interesting change. Because the period of this graph has shortened, you will expect it to cross the x-axis more frequently, which is exactly what it does. It crosses at 0, at 90, at 180, at 270, and 360. In other words, every 90 degrees. Yeah, that's quite a long list. The maximum value of the function, it goes up to 1, never goes higher than 1, so the maximum value is 1. And the minimum value is minus 1. You can see that it will never go below minus 1. This last question combines all the graphs that you've drawn. So you looked at the function y equal to sine x. Then you looked at the function y equal to 2 multiplied by sine x. So in the second function, you would calculate sine x and multiply it by 2. Or in the third function, you looked at y is equal to sine 2x. So over here, you double x and then you find the sine ratio. We can combine that into a general form and look at the function y is equal to a sine bx. So over here we looked at a, over here we looked at b, over there we've put the two together. If a is 1 and b is 1, you get y is equal to 1 sine 1x, which is just simply y is equal to sine x. And that is the graph that's been drawn over here. From your investigation, you should have seen that when you manipulate the value of a, which is this graph over here, you change the amplitude. And when you manipulated b, which is this graph over here, you changed the period. As a conclusion to these investigations, I'd like you to think about two things. What will the graph of y is equal to minus sine x look like? In other words, we've made a negative 1. And what would the graph of y is equal to sine of a half x look like? In our next set of investigations, you will be looking at the functions y is equal to a cos x bx and y is equal to a tan bx.